Welcome, Russ. I'm really glad you could join us here today.
Thank you. Thank you, Andrew.
So, today you're the Director of Research at Apple, and you also have a faculty, a professor at Carnegie Mellon University. So I'd love to hear a bit about your personal story. How did you end up doing this, deep learning work that you do?
Yeah, it's actually, to some extent, it was, I started in deep learning to some extent by luck. I did my master's degree at Toronto, and then I took a year off. I was actually working in the financial sector. It's a little bit surprising. And at that time, I wasn't quite sure whether I want to go for my PhD or not. And then something happened, something surprising happened. I was going to work one morning, and I bumped into Jeff Hinton. And Jeff told me, hey, I have this terrific idea. Come to my office, I'll show you. And so we basically worked together, and he started telling me about, these Boltzmann machines and contrastive divergence and some of the tricks which I didn't at that time quite understand what he was talking about. But that really was very exciting and really excited me. And then basically within 3 months, I started my PhD with Jeff. So that was kind of like the beginning, because that was back in 2005, 2006, and this is where some of the original deep learning algorithms using restricted Boltzmann machines and supervised pre-training were kind of popping up, and so that's how I started. It was really that one particular morning when I bumped into Jeff completely changed my future career moving forward.
And then, in fact, you were a co-author on one of the very early papers on restricted Boltzmann machines that really helped with this resurgence of neural networks and deep learning. Tell me a bit more what that was like, working on that seminal.
Yeah, this was actually a really this was exciting year. It was my first year as a PhD student, and Jeff and I were trying to explore these ideas of using restricted Boltzmann machines and using pre-training tricks to train multiple layers. And specifically, we were trying to focus on autoencoders. How do we do nonlinear extension of PCA effectively? And it was very exciting because we got these systems to work on MNIST digits, which was exciting. But then the next steps for us were to really see whether we can extend these models to dealing with faces. So remember, we had this Olivetti faces data set. And then we started looking at, can we do compression for documents? So we started looking at all these different data, real valued, count, binary. And throughout, a year, it was, I was a first-year PhD student, so it was a big learning experience for me. But really within 6 or 7 months, we were able to get really interesting results and really good results. Something that we were able to train these very deep autoencoders. This is something that you couldn't do at that time using sort of traditional optimization techniques. And then it turned out into a really exciting paper for us. That was super exciting year because it was a lot of learning for me, but at the same time the results turned out to be really impressive for what we were trying to do.
So in the early days of this resurgence of deep learning, a lot of the activity was centered on restricted Boltzmann machines and then deep Boltzmann machines. There's still a lot of exciting research there being done, including some in your group, but what's happening with Boltzmann machines and restricted Boltzmann machines?
Yeah, that's a very good question. I think that in the early days, the way that we were using restricted Boltzmann machines is you sort of can imagine training a stack of these restricted Boltzmann machines that would allow you to learn effectively one layer at a time. And there is a good theory behind, when you add a particular layer, it improves the variational bound and so forth under certain conditions. So there was a theoretical justification, and these models were working quite well in terms of being able to pre-train these systems. And then around 2009, 2010, once the compute started showing up, GPUs, then a lot of us started realizing that actually directly optimizing these deep neural networks was giving similar results or even better results.
So just standard backprop without the pre-training of restricted Boltzmann machine.
That's right. And that's sort of over 3 or 4 years, and it was exciting to the whole community because people thought that, wow, you can actually train these deep models using these pre-training mechanisms. And then, with more compute, people started realizing that you can just basically do standard backpropagation, something that we couldn't do back in 2005 or 2004 because it would take us months to do it on CPUs. And so that was a big change. The other thing that I think that we haven't really figured out what to do with Boltzmann machines and deep Boltzmann machines. I believe they're very powerful models because you can think of them as generative models. They try to model complex distributions in the data. But when we start looking at learning algorithms right now, they require using Markov chain Monte Carlo and variational learning and such, which is not as scalable as backpropagation algorithms. So we yet have to figure out more efficient ways of training these models, and also the use of convolution. It's something that's fairly difficult to integrate into these models. I remember some of your work on using probabilistic max pooling for sort of building these generative models of different objects and using these ideas of convolution was also very, very exciting, but at the same time, it's still extremely hard to train these models. So
it's Honlack-Lee's work.
Yes, Honlack-Lee's work, right? And so we still have to figure out what are on the other side, some of the recent work using variational autoencoders, for example, which could be viewed as directed versions of Boltzmann machines. We have figured out ways of training these models. Was a work by Max Welling and Dirk Kingma on using reparameterization tricks. And now we can use backpropagation algorithm within the stochastic system, which is driving a lot of progress right now. But we haven't quite figured out how to do that in the case of Boltzmann machines. So
that's actually a very interesting perspective that I actually wasn't aware of, which was that in an earlier era where computers were slower, that the RBM pre-training was really important. It was only faster computation that drove switching to standard backprop. In terms of the evolution of the community's thinking in deep learning, another topic that I know you spent a lot of time thinking about is the generative, unsupervised versus supervised approaches. Do you share a bit about how your thinking about that has evolved over time?
Yeah, I think that's a really, I feel like it's a very important topic, particularly if we think about unsupervised or semi-supervised or generative models, because to some extent, a lot of successes that we've seen very recently is due to supervised learning. And back in the early days, unsupervised learning was primarily viewed as unsupervised pre-training because we didn't know how to train these multi-layer systems. And even today, if you're working in a settings where you have lots and lots of unlabeled data and a small fraction of labeled examples, these unsupervised pre-training models, so building these generative models can help. For supervised tasks. So I think that a lot of us in the community, it's kind of like was the belief when I started doing my PhD, it was all about generative models and trying to learn these stacks of models because that was the only way for us to train these systems. Today, there is a lot of work right now on generative modeling. If you look at generative adversarial networks, if you look at variational autoencoders, deep energy models is something that my lab is working on right now as well. I think it's very exciting research, but perhaps we haven't quite figured out. Again, for many of you who are thinking about getting in the deep learning field, this is one area that I think we'll make a lot of progress in, hopefully in the near future.
So unsupervised learning.
Unsupervised learning, right. Or maybe you can think of it as unsupervised learning or semi-supervised learning, where I give you some hints or some examples of what different things mean, and I throw you lots and lots of unlabeled data.
So, that was actually a very important insight that in an earlier era of deep learning where computers were just slower, the restricted Boltzmann machine and deep Boltzmann machine that was needed for initializing the neural network weights, but as computers got faster, straight backprop then started to work much better. So, one other topic that I know you've spent a lot of time thinking about is the supervised learning versus generative models, unsupervised learning approaches. So, tell me a bit about how your thinking on that debate has evolved over time?
I think that we all believe that we should be able to make progress there. It's just All the work on Boltzmann machines, variational autoencoders, GANs, you can think a lot of these models as generative models, but we haven't quite figured out, how to, really make them work. And how can you make use of large volumes? And even for, I see a lot of in IT sector, companies have lots and lots of data, lots of unlabeled data. There's lots of efforts for going through annotations, because that's the only way for us to make progress right now. And it seems like we should be able to make use of unlabeled data, because it's it's just abundance of it, and we haven't quite figured out how to do that yet.
So you mentioned for people wanting to enter deep learning research, unsupervised learning is an exciting area. Today, there are a lot of people wanting to enter deep learning, either research or applied work. So for this global community, either research or applied work, what advice would you have?
Yes, I think that one of the key advices I think I should give is people entering that field. I would encourage them to just try different things and not be afraid to try new things and not be afraid to try to innovate. I can give you one example, which is when I was a graduate student, we were looking at neural nets, and these are highly non-convex systems that are hard to optimize. And I remember talking to my friends within the optimization community, and the feedback was always that, well, there is no way you can solve these problems because these are non-convex. We don't understand optimization. How could you ever even do that? Compared to doing convex optimization. And it was surprising because in our lab, we never really cared that much about those specific problems. We're thinking about how can we optimize and whether we can get interesting results. And that effectively was driving the community. So we were not scared. Maybe to some extent because because we were lacking actually the theory behind optimization. But I would encourage people to just try and not be afraid to try to tackle hard problems.
Yeah, and I remember you once said, don't learn to code just into high-level, deep learning frameworks, but actually understand.
Yes, that's right. I think that it's one of the things that I try to do when I teach a deep learning class is one of the homeworks. I'm asking people to actually code backpropagation algorithm for convolutional neural networks, and it's painful, but at the same time, if you do it once, you really understand how these systems operate and how they work, and how you can efficiently implement them on GPU. And I think it's important for you to when you go into research or industry, you have a really good understanding of what these systems are doing. So it's important, I think,
Since you have both academic experience as a professor and corporate experience, I'm curious, if someone wants to enter deep learning, what are the pros and cons of doing a PhD versus joining a company?
Yeah, I think that's actually a very good question. In my particular lab, I have a mix of students. Some students want to go and take an academic route. Some students want to go and take an industry route. And it's becoming very challenging because you can do amazing research in industry, and you can also do amazing research in academia. But in terms of pros and cons, in academia, I feel like you have more freedom to work on long-term problems, or if you think about some crazy problem, you can work on it. So you have a little bit more freedom. At the same time, the research that you do in industry is also very exciting because in many cases with your research, you can impact millions of users if you develop, a core AI technology, and obviously within the industry you have much more resources in terms of compute and be able to do really amazing things. So there are pluses and minuses. It really depends on what you want to do. And right now it's very interesting environment where academics move to industry, and then folks from industry move to academia, but not as much. And so it's very exciting times.
It sounds like academic machine learning is great and corporate machine learning is great, and the most important thing is just jump in, right? Either one, just jump in.
So it really depends on your preferences, because you can do amazing research either place.
So you've mentioned unsupervised learning as one exciting frontier for research. Are there other areas that you consider exciting frontiers for research?
Yeah, absolutely. I think that what I see in our community right now, particularly in deep learning community, is there are a few trends. One particular area that I think is really exciting is the area of deep reinforcement learning, because we were able to figure out how we can train agents in virtual worlds. And this is something that's, in just the last couple of years, you see a lot of progress of how can we scale these systems, how can we develop new algorithms, how can we get agents to communicate to each other, with each other, and it's, I think that area is, and in general the settings where you're interacting with the environment is super exciting. The other area that I think is really exciting as well is the area of reasoning and natural language understanding. So can we build dialogue-based systems? Can we build systems that can reason, that can read text and be able to answer questions intelligently? I think this is something that a lot of research is focusing on right now. And then there's another sort of sub-area also, is this area of being able to learn from fewer examples. So typically, people think of it as one-shot learning or transfer learning, a setting where, you learn something about the world, and I throw you a new task at you, and you can solve this task very quickly, much like humans do, without requiring lots and lots of labeled examples. And so this is something that's a lot of us in the community are trying to figure out how we can do that, and how can we sort of come closer to human-like learning abilities.
Thank you, Russ, for sharing all the comments and insights. So it was especially interesting hearing the story of your early days doing this.
Thanks, Andrew. Yeah. Thanks for having me.